All right, so guys, I want to address a few details that weren't really covered in the first video. And the first one of those is that torque, and now this is just a reminder, this symbol is a tau that we're going to use to represent torque. It's actually a vector. And we're going to define it in a way that's going to seem weird at first, but as we start to continue studying angular motion and we get into like looking at objects that are actually rotating, this is going to make more sense. So let's go ahead and say we have some object. I'm just going to take a wheel. Let's say it's fixed, so it has to rotate about this point. You could imagine like a bicycle wheel or something, and this is the axle. And let's say we push on it right here. Well, if we push there, this thing is going to want to rotate in the counterclockwise direction, right? It's going to want to rotate this way. Well, when it comes to defining what direction this torque is, right, there is a torque, because here's our lever arm, and the magnitude of that torque is just going to be equal to R times F, like I have there. I guess I don't need to write it again. When it comes to defining the direction of that torque, well, it doesn't really matter what direction this force is in. The thing that matters is the direction it's making this thing spin. And that can be a weird thing to try to define, because if you think about it, different points, right? Like if we pick a point here, well, that point on this object is actually moving that way, right? If we were to draw a velocity vector. If we pick a point, let's say over here, well, that point on this object is actually going to be moving in that direction, right? So all of these different points on the object are actually moving in different directions. But we still need to find a way to call this direction of rotation. We need to find a name for this. We need to find a direction to give this rotation. And we're going to do that using something called the right-hand rule. So in order to define the direction of this torque, you're going to think about the way it's going to make the object want to rotate and curl your fingers in that direction. So here, the force is this way, right? It wants to make the object rotate this way. So if I curl my fingers this way, my thumb points up. The direction of that rotation is actually out of the board. So this torque, the torque exerted by this force, is out of the board, which can seem a bit weird, but it makes sense if you think of it as being defined as parallel to the axis of rotation. Right, so you can imagine an axis here coming out of the board, and our object is actually rotating around that axis. And our torque vector, right, the direction of the torque caused by this force, is along that line, coming out of the board. So let's go ahead and maybe look at a quick example. So let's say I have a rod, and it's fixed to rotate about this axis, and I exert a force here, maybe call that F1. Let's say I exert another force here, call that F2, and I exert another force here, F3. And I'm going to go ahead, and we can always choose which way we decide to call positive or negative. I'm going to go ahead and try to call, let's call in to the board the positive direction. And then let's think about the different torques caused by each of these. So F1 is pushing this way. If our rod is fixed at this point, so it has to rotate about this point, well, F1 is making it want to turn this way. So if I apply my right-hand rule, right, it's trying to make it rotate that way, which is into the board. So then I guess we could say the torque caused by F1 would be positive. What about the torque caused by F2? Well, F2 is pushing that way. It's trying to make it rotate in the other direction. So, oh, marked my hand. So F2 would actually be negative. So the torque caused by F2 is negative. And the torque caused by F3, right, if we look at F3, here it's pushing down, and it wants to make it rotate this way. So F3 is actually trying to make it rotate in the positive direction also. So the torque caused by F3 is also positive. Now, if we wanted to figure out which way this thing is actually going to rotate, we would have to sum all of these torques. And to do that, we actually have to learn a little bit more. So we don't know whether the net torque is going to be positive or negative until we can actually learn how to calculate torques that are acting at angles like this. And we're going to talk about that right now. So let's go ahead and say let's take another rod. Let's say this is our axis of rotation. And let's go ahead and say that we exert a force on it, well, right here. And we want to figure out the torque done by that. Let's go ahead and say that it is acting at a distance r from the axis of rotation. So r is our lever arm. Well, if we want to calculate the torque on this object by this force, well, we don't want to just take r times F. And the reason for that is that there are two components. And both of these components are not going to actually give a torque. So if you think about it, this component here is not going to help make this thing rotate. Right? This component here is just pulling outwards. It's not making it spin. So this component is not going to exert a torque, but this component is. Right? So we'd have to, I guess, define an angle. Let's call this theta. This would be F cosine theta, and this would be F sine theta. The torque exerted by this force would actually be R times F sine theta. That would be the magnitude of the torque. And it would be in this direction, out of the page. Right, here's our axis of rotation. This force is making it want to rotate that way, out of the page. So this is an example where the force, it's actually exerting less torque than it would be if it was pushing on it straight in that direction. Right? And you can imagine if we had a situation where you exerted a force on this object and you just pulled this way. Right? No matter how hard you pull, you're not going to make this thing rotate. This force is not exerting any torque at all because it doesn't even have a component in this direction or in this direction. So that's how we can calculate the torque acting at an angle.